When I was a student, there were a very propagated paradigm that mathematical physics, then the sign of the identical equality, partial differential equations. Certainly, it did not mean that only equations known from the general university course are important. There are equations do not belonging to any of three famous types: elliptic, parabolic, and hyperbolic. And there are nonlinear equations, etc. But anyway, it was considered that the diversity of differential equations is enough to cover all models of mathematical physics, and even all models, maybe apart from discrete models, of objects from the great world surrounding us. Well, now 40 and even more than 40 years are past, and we know that it is not enough to restrict our consideration only by differential equations. To cover all, and even not all, but there are many phenomena in the surrounding world that differential equations are not enough to describe them. And apart from differential equations, we have to consider and to investigate functional differential equations that are equations containing, apart from differential operators acting on the desired function, containing operators of another nature, such as translation operators, integral operators, operators restricting or extending or expanding the independent variable, etc. This is absolutely justifiable because all differential equations link the desired function and its derivatives pointwisely. So all contained in the left part of the equation, in the left-hand side of the equation, and everything contained at the right-hand side of the equation are linked at the same point. And in this case, all the phenomena where we have to link their values at different points do not get into our scope. This is very general explanation of the motivation to study functional differential equations. And this is contained in my item 1. So, functional differential equations are to be investigated because, this is contained in my item 3. Functional differential equations are to be investigated because there are many applications not covered by the classical theory of differential equations. Another reason is that qualitatively new phenomena not not found and not taking place in the classical theory of differential equations arise in this area. And one more reason, and it is very important as well, because a number of classical research methods very good developed in the direction of differential equations turn out to be inapplicable in the case of functional differential equations. For example, let me try to write something down. How to do it in Zoom. Okay, I was told that Zoom has its own blackboard. Is it true? No, there is no such a possibility. Just a second. Do you see this whiteboard? Or you see only my presentation?
We see just presentation.
Okay. Then let's live in the framework of it. Suppose that we take a differential equation of any order and add just one term like u, which is the desired function of t, let it be even ordinary differential equation. So we take a differential equation of any order and add just one translated term, u of t plus h. It looks like we add a small perturbation to a very well-known object. But it is not true, because if you expand this u of t plus h into the Taylor series, then you will see that it contains the derivative of each order. More strictly, this additional term is indeed the translation operator is unbounded, unlike differential operators, but it is neither compact operator nor finite dimensional one. And this generates...
You see all the second pages.
Excuse me? I have no. I still have no intention to browse the page. I intentionally remain on the first page, on the first slide. So this example with the additional term, which cannot be treated as a small perturbation, illustrates illustrates all my 3 points. Functional differential operators are investigated for a very long time. Examples of their investigations can be found even in works of Euler. But when we speak about its contemporary situation, then regarding ordinary differential equations, it is reasonable to mention such author as Anatoly Dmitrievich Myshkis. But today I am going to speak about partial functional differential equations, and probably the most important pioneering work is this paper of Hartmann and Stampakia of 1966. Now let me substantially restrict the scope, and from this point I shall speak only about differential difference equations. They are functional differential equations such that only differential operators and translation operators act on our desired functions. What is important for this class of functional differential equations? First, translation operators are Fourier multipliers as differential ones. This allows us to apply the classification of equations known for classical partial differential equations. Because, well, you say, if you can say that such a differential difference operator is elliptic, then you immediately can substantially define equations of parabolic and hyperbolic type. And if since each differential difference operator is a Fourier multiplier, then you can define its ellipticity via the sign of the real part of its symbol. The general theory of such equations is can be found in these 4 books. Well, I say book even about a journal paper if it occupies the whole volume of the journal. So if a person would like to find out more about this direction, about the general theory, then I would advise to read these 4 books and to add their bibliographies. Then a certain impression would be obtained. Now, I restrict our consideration for today even more. We will discuss only parabolic differential difference equations, and we will consider the Cauchy problem for such equations. I would like to draw your attention to previous papers in this direction. They are written by Vladimir Rabinovich. That time he worked in Rostov. Now he worked in Mexico, and in these papers, results were obtained for solution from Sobolev spaces, more exactly from weighted Sobolev spaces. But today I would like to draw your attention to the case where solutions are classical. What is the reason to be interested to look for classical solutions? The reason is that, as we know from the classical theory of parabolic equations, I mean differential parabolic equations, we know that there is a very interesting phenomena specific especially for parabolic equations. This I mean stabilization. And the stabilization mean a certain behavior of the solution at low order manifolds, even at manifolds of at low dimensional manifolds, even on manifolds of dimension 1. And to deal with this phenomena, we have to define, we need traces of solutions on low dimensional manifolds. You know that the existence of such a trace is not guaranteed if the solution belongs to a Sobolev space. So this is the motivation to deal with classical solutions. Let us consider the first case of parabolic differential difference equation, of parabolic differential difference equations. Consider equations of type 1. So you see here each h is a vector from Rn. They are mutually orthogonal, they are normed, and the coefficients ajk and bjk are just real constants. There is a temptation to treat the second term of the right-hand side of the equation as a low-order term, because, well, the first term has order 2, but in the second term, we have only the desired function itself, so the zero-order derivative of it. But as I told earlier, this translation makes this term, let me say, a term of the same strength of the first one. So in this theory, we do not use the term equations with low order non-local terms. It is correct to classify these equations in another way. In this case, we have the sum of differential operator and translation operator. Oppositely, let me get forward for a moment. Another case is an equation of this type. You see, here we have the superposition of differential operators and translation operators. So this is the correct classification and the natural classification for differential difference equations. And you will see the qualitative difference below. So what is done for the problem 1, 2? The function 3, where the function e calligraphic is defined by this relation, is the unique classical solution of problem 1, 2 bounded in each such layer. For a second, I get back to the problem 1, 2. So this is the solution of this problem, bounded in each such layer. Note that this theorem, which is actually the unique solvability theorem and the theorem on the integral representation of the solution, this theorem is valid without any additional assumptions about coefficients and other parameters of the equation. When we pass to the asymptotic behavior of solutions, we have to impose additional restrictions. To do that, we introduce the notion of strong ellipticity. So we say that a differential difference operator acting in Rn is said to be strongly elliptic in Rn if there exists a positive constant c such that the symbol of our operator, R of psi, satisfies this inequality for each psi from Rn. So the symbol is, the real part of the symbol is bounded from below by the second power of the absolute value of our dual variable. And the theorem of about the asymptotic behavior of solutions is as follows. We assume that such an operator is strongly elliptic in Rn, where L calligraphic is the following operator, where L calligraphic acts as follows. If we compare operator L calligraphic with the operator from the right-hand side of our equation, look, this one and this one, then we see that we take the right-hand side of our investigated equation and discard all terms with non-negative coefficients. And once we impose this restriction, then the following limit relation holds for each x from Rn. So the weighted solution minus the function w of these independent variables. I shall explain what is w a bit later. So look, we have the following weight function for our solution, and we have the following transformation of the independent variables of the spatial variables for our echelon function, which is used to compare the behavior of the investigated solution and the behavior of the echelon solution. And what is echelon solution in our case? It is the bounded solution of the Cauchy problem for the heat equation, just for the equation du over dt is equal to the Laplacian of u, with the initial value function u0 of p1, x1, etc., pn, xn. u0 is our original initial value function, yeah, but it is taken at this point where pj is defined as follows and qj is defined as follows. And please note that the strong ellipticity condition for this operator guarantees the non-negativity of this expression under the square root. So if theorem 1 is a unique solvability theorem and a theorem about integral representation of the solution, then theorem 2 is the theorem of the weighted asymptotic closeness of solutions. So we take an echelon function, which is a very well known. This is a solution. This is the solution of the Cauchy problem for the heat equation, and prove that if we multiply our investigated solution of the non-local problem, by this weight, then their difference will tend to zero as t tends to infinity. Now the case of superpositions of differential and translation operators. We consider this equation, so you see that now differential and translation operators form a superposition instead of sum as before. Here ajk and bjk are again real coefficients. ej is the unit vector of the coordinate direction number j, and the integral representation of the solution is again 3. So we have the convolution of this kernel. I think it is quite natural to say it, to call this a Poissonian kernel or a Poisson-like kernel, and it convolutes with the initial value function. But in this case, the Poissonian kernel is naturally else. So it is computed as follows. The kernel has the following form now. So this function 4 satisfies our Cauchy problem in the sense of generalized functions, or if you like, distributions. But in the half space Rn times the interval 0 plus infinity, it satisfies our equation in the classical sense, and so the sense is the substance is as follows. It satisfies the Cauchy problem in the sense of generalized functions. But once we leave the initial hyperplane, the solution immediately becomes classical. And the uniqueness is preserved, so there are now no other solutions of problem 4.2 in the sense of generalized functions. This was the unique solvability theorem and the theorem on the integral representation of the solution. Now the theorem of the asymptotical behavior is as follows. If the assumptions of theorem 3 are satisfied, let me get back to those assumptions. So we impose the strong ellipticity assumption for the whole operator L from the beginning. So we need it not only for the asymptotic behavior of the solution, but already for the solvability. And if this assumption is satisfied, then this limit is equal to 0 for each x from Rn, where v of x t is the bounded solution of the Cauchy problem for this differential equation. This is already a differential parabolic, classical parabolic differential equation with the same initial value function u0. Now we do not transform its independent variables, and pk for each k is defined as follows. And you see, we do not know yet that this solution, this classical differential solution, is parabolic. But once we assume that our operator minus L is strongly elliptic, then it guarantees the parabolicity of this our equation. So these are the results, and now I would like to say a few words about how to prove this. Of course, I cannot provide you the whole proofs, but I hope to be able to share main ideas laying in their base. So what is the proof technique? To find the Poissonian kernel, we formally apply the Fourier transformation with respect to the n-dimensional variable x to the original problem. And we get the Cauchy problem for a first-order ordinary differential equation. So, look, we had a partial differential difference equation. Once we apply the Fourier transformation, we get an ordinary differential equation. depending on the n-dimensional parameter psi. In particular, equation 1, let me get back. This equation goes into this differential equation, ordinary differential equation. And equation 4 gets into this ordinary differential equation. We can solve them. They are just ordinary differential equations with constant coefficients. So we solve the Cauchy problems for those equations, formally apply the inverse Fourier transformation to those solutions, and we get function 3, this one, in both cases. Just kernels are different. Just the kernels E calligraphic are different. And this function 3 is the integral representation of the solution of the original problem. Since this point, the function E calligraphic, which is the kernel of this integral representation, is known to us. And now we have to justify all the previous actions. Because they are not justified, we formally applied the Fourier transformation and we formally applied the inverse Fourier transformation. Now we have to justify it. But we do not justify the applying of our Fourier transformations. Instead, we just take this function 3, which is already known for us, and directly substitute it in our original equation. And to do that, what should we do? First, we have to prove that this function 3, which is the convolution of the Poissonian kernel and the initial value function, we have to prove that it is well defined in this half space. Second, we have to prove that this convolution satisfies, in the classical sense, the original equation in the same half space. And secondly, and third, we have to prove that convolution 3, First, we have to prove that the Poissonian kernel is well defined. Second, we have to prove that the Poissonian kernel satisfies the original equation in the same half space. And then we have to prove that not only the kernel, but its convolution with the initial value function is well defined in the same half space and admits the differentiating inside the integral. Once we prove that it admits the differentiating inside the integral, we already have everything, because we already proved that the kernel satisfies the original equation. So the first and the second step are rather obvious. Maybe it requires certain calculations, but this is just a homework. The last item has to be clarified. So for each fixed positive t, we have to prove a sufficiently fast decay of the function e calligraphic of the kernel and its corresponding derivatives as the absolute value of x tends to infinity. Let me show how to do this for our equation 1. So for for the kernel of this form, for the kernel of this form. If n is equal to 1, then we decompose the function, then we decompose the kernel into its even and odd summands, reduce each of them to this form, to form 5, where f belongs to L infinity on the positive half line, while psi belongs to L1 over the positive half line. And then we apply the following corollary from the famous Wiener-Toberian theorem. The last integral tends to 0 as x tends to 0. Let me place it this in order everything to be seen. So the last integral tends to 0 as x tends to 0 if there exists a function psi 0 from L1 such that its Mellin transform is defined on the whole axis R1 and has no real zeros. And this limit is equal to 0. In our case, the function e to the power minus t eta square can be taken as psi 0 for both summands. Then we integrate by parts to reduce the product x to the power 2 e calligraphic to form 5 again. And this proves a sufficient decay rate of our kernel. Then we repeat the above procedure for its corresponding derivatives and complete the proof for this step. If there are more than one spatial variables, then no intermediate usage of the Wiener-Toberian theorem is possible because we deal with a multidimensional integral and we know that all Toberian theorems are one-dimensional. But in this case, we use the presence of special directions of the problem. They are determined by translation vectors contained in the equation, and iterate the decomposition of the integral into plane waves. Generally, the amount of those iterations is equal to the amount of non-local terms of the original equation, so the procedure has a finite number of steps. And once this procedure is completed, then we select a factor inside the integral coinciding with the function with the functional e calligraphic of the one-dimensional problem. And further, we apply the result obtained for it above. In equal 4, the problem is even easier. The integrand always contains such a factor bounded from above by a function of this kind. This is guaranteed by the ellipticity condition. I shall not speak about the proof of the uniqueness because actually all the task is to find a correct class of initial value functions, and this is done by my predecessors even for much more general type of the equation. And to prove the result on the asymptotical behavior of the solution, we use the method modestly called by Stein and Weiss as the decomposition of the integral into its big and small parts. So we take this difference, yeah, we represent it by this sum, where A is a positive parameter and Q of A is a cube centered at the origin with edge of length A. And then we reduce the integrand into the form such that to estimate this term, we use the boundedness of the integrand, and to estimate the another term, we use the limit properties, the limiting properties of the integrand. This technique is rather well known to explain all the detail. Well, I'm afraid the time of my presentation is not enough. So let me just stop here in order to preserve a certain time for possible questions. So thank you very much for your attention.